Hi, my name is Luke and I'll present an overview of the paper Evolving Visual Counterfactual Medical Imagery Explanations with Cooperative Coevolution Using Dynamic Decomposition. This work is a collaborative effort between my colleagues and I, whose names you'll see on the slides. This presentation will provide a high-level overview of our novel approach to enhancing explainability in black box medical diagnostics using cooperative coevolutionary algorithms with dynamic decomposition. Explainable AI is a subfield of artificial intelligence focused on making AI systems more transparent and understandable. In healthcare, XAI is important because it can help medical professionals trust and understand the decisions made by black box models in medical diagnostics. Counterfactual explanations are a specific type of post hoc XAI methods that propose hypothetical alternatives to a given data point, typically in the form of a statement speculating what could happen under different circumstances, and demonstrating how different circumstances may lead to different outcomes. An example of a counterfactual in an image-based classification problem could be modifying input data, such as features in an X-ray image, to see how these changes affect the model's prediction, providing insight into the model's reasoning process. An example of this process is shown in the image. Image A depicts a digit currently classified as a 7. By inserting the red pixels in image B, we create a counterfactual seen in C, which when reclassified now is predicted to be a 9. Generating counterfactuals for medical images is challenging, primarily due to the large number of pixels involved. Using a cooperative coevolutionary approach, we transform visual counterfactual generation into an optimization problem. We aim to minimally alter medical images to change a model's diagnosis, evolving images from class A to B with the fewest changes. Using a divide and conquer strategy, cooperative coevolutionary approaches can decompose complex images into smaller, more manageable image segments, each optimized by a dedicated population focusing on specific image areas for targeted modification. However, identifying critical segments within medical images is challenging due to each case's uniqueness. Segments crucial in one image may be irrelevant for another, necessitating a dynamic decomposition approach. To solve this, we employ a cooperative coevolutionary algorithm with a novel dynamic hierarchical problem decomposition approach we've named the M-tree CCEA. Our approach dynamically decomposes an image into smaller sections throughout the algorithm's execution, enabling the algorithm to focus on and modify critical features without prior knowledge of the location of these pixels. Therefore, the optimization process is twofold, simultaneously evolving the image's optimal decomposition and optimal localized changes within these sections, collectively forming the entire counterfactual. Our experiments used two datasets, a reduced MNIST, which consists of handwritten digits 7 and 9, where the goal is to evolve minimal changes to a 7-digit to reclassify as a 9, and a diabetic foot osteomyelitis dataset containing X-ray images, where the goal is to evolve changes to an image classified as negative for DFO to having DFO. The experiments used pre-trained classifiers, one being a dense network for MNIST and a fine-tuned VGG16 model for DFO classification. Our experiments compared the performance of our M-tree CCA algorithm with a genetic algorithm. When comparing fitness scores, the M-tree CCA and genetic algorithm perform similarly on the smaller MNIST images. However, in the more complex DFO dataset, our M-tree CCA outperformed the genetic algorithm, achieving significantly better scores. On the right, you can see examples of evolved counterfactual images. Image A demonstrates image pairs from the MNIST experiments with the original image on the left and the counterfactual evolved on the right. Interestingly, the changes typically involved altering key features that distinguish the digits 7 and 9, such as lessening the prominence of the top horizontal line of the 7 and inserting pixels between the horizontal and vertical lines, forming a 9 shape. In the DFO images, modifications were subtle but significant, often focusing on areas along the bone edges where the DFO pathology is typically present. In summary, our M-tree CCA algorithm effectively evolved counterfactual images, a step forward in enhancing the explainability of black box AI models without lessening the predictive accuracy of the original model. I'll happily answer any questions if you can catch me at the conference.